My pleasure. Take care.
We're going to continue our session we're on track to next talk. And let me introduce the speaker. The speaker we have here is Dr. Craig Rieger. 1 second. Craig, can you unshare your screen so I introduce you in the bio so we can show the bio? Yeah, thank you. So Dr. Craig Rieger is our next speaker, and he is a managing director for TRECS Consulting and a retired chief control system research engineer and directorate fellow at Idaho National Lab. Craig, backed by years of professional expertise in practical and theoretical control systems engineering, Dr. Rieger pioneered the resilient control systems research area with an interdisciplinary team at INL and several universities. Advancing this threat resilience theme is his current focus as a managing director of TRECS Consulting. Prior to establishing his consultancy, he worked for the Idaho National Lab in several positions, including as Directorate Fellow, Chief Control Systems Research Engineer, Control Systems Lead, and Instrumentation, Control and Intelligence Systems Lead. Despite retiring from INL, Dr. Rieger assists the laboratory transition technologies that his team developed before he left. Before embarking on his professional journey, Dr. Rieger earned a Bachelor of Science in Chemical Engineering from Montana State University, Bozeman. Subsequently, he returned to his alma mater and received a Master of Science in Chemical Engineering before completing a PhD in Measurements and Controls from Idaho State University. Throughout his career, Dr. Rieger has contributed to a number of publications, including Resilient Control Systems, Next Generation Design Research, a Cyber Resilient Design for Control Systems, and recently, this Wiley IEEE Book, Resilient Control Architectures for Power Systems. He also holds several patents in systems and methods for control system security. Although his career has been filled with highlights, he takes the most pride in establishing the interdisciplinary research area of threat resilient control system. In light of his team's achievement, Region 6 IEEE Directors Award was presented in 2014. The cornerstone of his success lay in many opportunities he has received over the years, in particular from INL, first in working as a practicing control systems engineer, and then to use this experience to advance control system resilience through a distinctive signature initiative. Looking toward the future, Dr. Rieger intends to see the technologies on which he has worked continue to mature. Dr. Craig, it is my honor to that you can be here and in this workshop, and appreciate your time. And Dr. Craig is also a member, Industry Advisory Board member for our center. So I appreciate all the mentorship what Craig is offering. So Craig, it's your turn, and you can share your screen.
All righty, thank you, Prakash. So I think it was implied in that description, and just like Andrew had said, I need to start sending out shorter bios because the MC feels that they have to give the whole thing. So most of us could do the same kind of thing. The book came about because we had actually been offering a special topics course. The University of Idaho actually has it as a catalog course, and the interdisciplinary research, which actually takes a lot of professors. Obviously, no one discipline can really inform all of them. It's actually wanting to, in many ways, develop the conversation between the disciplines. And it's more than multidisciplinary, which we've done for decades in projects. Any building project has mechanical, electrical, and others. It's really learning enough about what the other disciplines provide, how they communicate. I know even between engineers, we talk about the same subject with different nomenclature, which kind of messes with us. How do we get closer to that interdisciplinary aspect that will then make us more effective in achieving resilient solutions? What are the seams between the disciplines? And so today I'm going to talk briefly about some of the background with the resilient control systems, the precepts for it in architecture for resilient design. And as Prakash alluded, this was done when I was working for INL. I had a real opportunity to really evolve from a practical control engineer, a practicing control engineer, to leading a team to think about, okay, well, all that stuff that I maybe didn't think about when I was a practicing control engineer, like overloading people with too much data. Yeah, you really need to deal with that because it's not just about cyber threats. It's how do you better utilize the humans? And I'm very grateful that Ron Boring is going to be giving a talk more about that. So I'll leave it for him to talk about. But getting into the background, I'll talk about some of these areas. So control systems are very interconnected. They're based upon feedback loops with the power grid. Oftentimes that's a supervisory control, which is a human. A control engineer would think supervisory control is automated, which is why language is important. You need to understand what's going on. But we integrated a lot of this interconnectivity, and we didn't realize that the fact that we're doing this is creating so much complexity that things can go wrong. Think August 2003 blackout and those since. The Swiss cheese model, the holes line up and all of a sudden, bang, you have a big problem. Moving towards resilience, we need to get away from that complexity as much as we can. It will still exist, but how do we bin it? From a cybersecurity perspective, Andrew, prior speaker, talked a bit about some of the solutions that are there, but even the techniques are evolving to and have evolved to more modular aspects, more intelligent aspects, and more people have access to them. And not necessarily the best and brightest in this field have access to these techniques that are built by nation state actors and things like that. So the threats are getting worse. I just heard something here yesterday that the hospital that I interact with, they were hit, and it's just going to continue to ramp up. I alluded to the human system aspect. So even when I was a control engineer in the 80s, we tried to do smart alarming, meaning we wanted to prevent 50 alarms that said one thing. You have a problem, give them one alarm, give them more information on what it is. You can't necessarily get alarm summaries down to 0, but you try to prioritize them so the operators know how to focus. It's amazing to me how well these people do with all the stuff we throw at them. And I've seen screens that are more overloaded than this one, by the way. So we need to get information to them. And as we start talking about moving to a more autonomous environment, well, you still have to worry about the design people, right? Because they're not perfect either. And how do those operators that you expect to deal with emergent aspects, how do you continue to evolve that since they're not interacting with the system maybe as much? How do you maintain that capability? Here again, things that Ron, Dr. Boring can talk about later. And so we've heard about reliability. John talked about reliability. Everybody understands what reliability means, and it has different forms. Some are built into the technologies. So I worked on control systems, as I said, and I had systems that were up for a decade. We even did all the maintenance. Everything was redundant. Did that all online. But we took it down one time just because we had to change out the whole new power system. We went to a modular power system, but they're extremely reliable. They're not resilient. I talked about the fact that we had a lot of interdependencies between domains, between control systems, and those just lend to complex failures. And in moving to more distributed control, what we're thinking about is how to bend those dynamics more specifically. I'll talk more about this when we get to a page that refers to multi-agent design, but I believe that's the future. And as an example to you, I'll talk about chemical plants. So for eons, long before we had digital control systems, they ran chemical plants successfully. And how did they do that? They had one, what they called unit operation after another. Within each unit operation, they've been the dynamics. So it's a fractionator. You got lots of controls in that fractionator. You've got reboiler controls, you've got condenser controls, you've got level controls, et cetera. But between it and the downstream unit operation, we have flow that needs to be maintained within a band and possibly product quality. So very few dynamics between them. As we think about the power grid, the move to microgrids can effectively do that same kind of thing. It doesn't mean that the bulk grid is going to disappear in my lifetime, but it may mean how we think about how that grid is designed in the future, having more localized microgrids with the bulk grid, even when put into its own microgrid, because it's a intermittent type of generation, that bulk grid becomes extremely stable without disruptions. But we have microgrids generally for the high consequence kinds of items. Here again, you're now distributing generation closer to the loads, responses, including threat response, closer. When it comes to the human interaction, goal conflicts can be a real challenge, and it's how we design the system. You know, there's stability, security, efficiency. We're expecting that the operators and dispatchers will take care of all this for us, but how do we better enable them? How do we give them the state awareness of what's going on? How do we tell them that, hey, this has maybe got a cyber aspect to it. It's not just a physical aspect, which traditionally all control systems talk to in some way, even if it's a lot of raw data that the operator dispatcher has to interpret. And so we want to move to something that's more tailored to the operator, something that they can work with, and we can more effectively use the time that they have. When it comes to the intelligent adversary, the cyber attacker, we want to obfuscate the system. We want them to have to actually think about what they're doing, which includes the bots that they built. It isn't just one answer. The system changes enough. People talked about automated response, moving target defense, et cetera. Well, we have legacy control systems. You know, how do we move towards that kind of thing where the system is obfuscated as compared to the way they do it now, which is actually behind a perimeter defense? So I'm thinking a little bit more about resilience. One of the first things that we dealt with when we started the International Symposium on Resilient Control Systems in 2008, which is now Resilience Week. And in fact, tomorrow is the start of Resilience Week in National Harbor. You have to have metrics. If it's worthwhile, people need to be able to measure it. What's the value proposition? Many of those metrics are actually still in process, but they're important. They drive policy. How can we motivate moving towards resilience? We need to know how to measure. Here again, what's the benefit to me? If I invest in this, how does this improve the resilience of the power grid for me? You know, there's a business value to that. Some of that comes through incentives and some of that comes through regulation. From an actual system standpoint, we need to consider the cyber, the physical, and the cognitive. There's a human at the center of this for, you know, as long as I'm probably going to be alive, there's going to be some human element involved in these systems. And so you need to make sure that they have not just a physical awareness of what's going on, but also a cyber awareness. And how's that information fused so it's simple for them to respond? Because your dispatcher is not going to be a cyber expert. Dispatcher needs to know that there's a cyber aspect, but the cyber expert, cyber defender needs to be able to adequately work with the physical. They need to understand what's important on the physical side. Resist and respond. You have your cyber, control, and cognitive. We need to bring in a cyber feedback loop like we have a physical feedback loop. Some of that may be designed to use software-defined networks and other things to make changes, but you're talking about a dynamic physical environment. It can't cause worse problems than it's supposed to solve. And then from a resilient design standpoint, we're looking for graceful degradation within the architectures. They must be adaptive and agile relative to how they're designed. So if something fails, whether it's a sensor, actuator, because of a cyber attack, here again, it's not an opportunity for the attacker to make things worse for you. The system itself has to have that recognition and response. And some of that is through the human, so your actionable information that the human's responding. So a dispatcher working with a cyber defender, the roles are more complex than that, but just to give you an idea. So some of the precepts, the definition, which is out in the Wikipedia for resilient control systems, is the capacity to control the system maintains state awareness and an accepted level of operational normalcy in response to disturbances, including threats of an unexpected malicious nature. It starts with, okay, what happened to my system? You know, what are those things that are out there, even complexities that may affect the system? How do we reduce those complexities? How do we know what happened to the system? It comes through first fully characterizing that space, which includes cyber. You just don't have physical only like we've got now in control systems. You have cyber detection and how that interfaces. There's a certain amount of information that you could provide relative to the operator on, okay, this particular piece of equipment is affected, and it's affected, we believe, by cyber. The closer you can get to what the problem is, the more effective the person on the physical side will know, but also on the cyber side. They need to be working as a team. And then the design providing adaptive capacity and agility to some of these issues which may not be well characterized by traditional means. Your analytics, distributed analytics to better understand, even historic understanding right down to the endpoints. So some things will need to be automated. And as the future goes forward, to reduce the timescale of response, we need to be thinking about how do we get to an automated fashion. So cascading failure, I brought up the August 2003 blackout. That's certainly not the only thing that's happened since that we need to concern ourselves with. Complexity just exacerbates that. Cybersecurity, clearly a new paradigm for control systems. It's not that they haven't been dealing with that for over a couple of decades. People understand that it needs to be dealt with, but how do we engender new architectures to better enable the responses? And we need to have the expert, intelligent architectures to truly understand it. One of the areas that I worked in my last years at INL, but certainly still an interest, is cyber physical anomaly detection. We use the physical to supplement the cyber to give us a higher level of understanding. It doesn't mean that there will be a physical aspect to it, but then also to give physical context to the cyber aspect. And it happens through not just one method. We may have diverse indicators that are distributed with the system and how to do it right. IDSs are available for control system networks. They look at logs. What we looked at is how to get away from logs. Can we do this almost independent of where things sit on the system to better characterize what's going on? In moving towards more of an autonomous multi-tier architecture, we can also, I believe, maximize efficiencies, but suffice it to say, there's a trade-off between resilience and efficiency. Sometimes the most resilient system is not going to be, at least from a cost basis, efficient, because you may be actually using redundancy in equipment and things like that to give you more options, which cost more to buy, more to maintain. But ultimately, we're wanting to have faster and faster responses to threats within the system. So just kind of a head-to-head comparison. As I said, complex interdependencies and things like that, or the tradition of the control system world. We want to actually decompose these dynamics to semi-autonomous echelons so they work within their sphere of influence. The idea there is that, like the unit operation, it only has certain responsibilities, and those agents between those responsibilities can act semi-autonomously but it's easier for even the human designer to understand what the inter-agent dynamics are. There's not a complexity of threads going everywhere that one needs to think about. Metrics to confirm performance, a negotiated trade-off. So some of this should actually be done, especially when you're talking about the cyber feedback loop, actually at the design level. If we put these things in our environment, nobody's going to want to test it, or nobody's going to want to allow it into an operational environment until they know, okay, if we take this certain set of mitigation or mitigation options, is it going to cause a worse problem? Do you have a lot of traffic crossing segments that could cause a problem if we isolate a segment, things like that. Human interaction going from the complexity to actually even a human feedback loop. As Ron could tell you more about, eye blink rates and things like that. There's a whole lot of research that can be done and is being done to better understand how the human is. Your best operator may have had a bad night. Okay, how do you recognize that? Maybe the autonomy will come in and play a role. How does that autonomy get switched to? And fusion and prioritization, very important to make the human effective. And then active defenses, as I've talked about before, moving target defense, automated response. So the architecture for design, you need to characterize all those things that could affect the control system response. And then prioritize those through data fusion for a mixed initiative response, a human working with the autonomy. How does that look? Mixed initiative actually comes from the roboticists who have talked about it for years. The robots working with a human, they're self-aware, they don't get in each other's way, et cetera, et cetera. How does that work within a control system design? And we've looked at those types of things, but there's certainly a lot of evolution that needs to go forward. And then resilient control design is really that hierarchical system. Management coordination and execution management coordination are truly the management and like power system experts that would inform, what are the philosophical goals? How do we shift the systems, including maybe bulk grid power plants, to meet those goals? And the bottom layer is the execution layer, what I would consider supervisory control, but in this instance, more autonomous. And then there's a lot of consumers of the information. Speaking about gateways, one-way gateways, just give them what they need and don't allow them more access than they need. That concept is valid now. There's ways to deal with that now, but it's very important in the inherent control system design and resilience to consider that even more. So as I said, human intrinsic decisions more at the top. So what control engineers would think about hybrid control or event-based control. How would management interact with each other to make a decision that somehow gets its way down to the dispatcher and how they operate? They may be very high-level goals, but there's a goal there. And the power engineers, the SMEs understand how to shift the plant, the trajectories. They actually, take plants offline now, but if you're dealing with this after a major threat, how does that work? And can we put that into the control system design so the humans interact with the autonomy as compared to the operator being informed or the dispatcher being informed? And the execution layer, the time-based dynamics, that's really where everything happens. But now, as compared to an operator working solely with it, there's some autonomous level of interaction. Now, that's the future. It's good to know what the future looks like so you can take the right pathways to go forward, which is the resilient control system architecture. And so these are just some of the areas that we worked in at INL. Role-based cyber-physical state and context awareness. We've got patents in process relative to some of the things we've done, distributed cyber-physical anomaly detection, context-aware visualizations that included both a top-level graphic to bring together the cyber and the physical folks, but then dropping down into more specifics that are related to them. So a SIM, a security information event management for the cyber, and more of a task-based awareness for the dispatcher. If you've got to make responses, line crews, etc., what's the highest priority for the response when major things are happening? How long is it going to take to make that fix? Or are you just going to have them reset something or go out to the substation? There's only so many people, and time has to be a consideration in that. Stepping through a playbook, not just for the cyber side, but the physical side, is the application, or a simple way of defining the application as you get down to the lower tiers of how that operates. But it starts with a top level awareness. What's the root cause of this? Who needs to be involved? Infrastructure, trustworthy assessment, proactive control, that's where that anomaly detection occurs. And it can lean to autonomous reactions that are told to the dispatcher in the future as you go forward. Right now, it's probably just informing the operator and the cyber defender. I talked about multi-agent in the lower left here. And then finally, cyber detection and feedback again. What does that feedback loop look like? How do we do that in the context of a dynamic system? So, resilience has been around. Resilient control systems was coined in 2009. The Wikipedia was put up right after that by myself and my colleagues. We worked with a number of universities. Resilience Week came out of that. The two research areas, state awareness, resilient design, which here again, performance must be judged by metrics. And there's a lot of discussion that's still ongoing about metrics as you move from reliability to resilience. And the power grid, how do you measure it? More specifically, is it a measure that we can actively get, not some complex measure? It considers man-made and natural threats. There weren't a lot of definitions in the 2000 era on resilience, but man-made and natural threats is one of those that came to be. Man-made, of course, is your cyber, but also the human that's making unintended actions that could hurt you, not malicious. And we want to get away from cascading failures because of that kind of thing. And so the architecture, cyber physical trustworthiness assessment, context awareness, multi-agent design, as I referred to in a prior slide, those are all areas that we were looking at, but also would be applicable going forward. And with that, are there any questions? I think we have a few minutes.
Thank you, Dr. Craig, for your presentation. I appreciate your insight on resiliency. So we are now happy. We have 3 more minutes, so we can take some questions. Maybe I'll start with a question. I think in your last slide, Craig, you mentioned that the metrics needs to be accepted by, do we have resilience metric? If so, how would we, we have a lot of students and faculty or listening, some industries. So, a couple of questions, I'm going to load up there, where do they go for resources to look at for resiliency metrics, if there is any, because, and there are many literatures do talk about different types of resilience metric, what goes on to your mind when people talk about resiliency metrics?
Well, there's a lot of metrics that have been proposed. 6-7 years ago, there wasn't many, but now there's a lot of metrics that have been proposed, including through DOE programs, individual industries. So what I would say is not necessarily does one metric fit all cases, especially when you're thinking about control system performance as compared to how a utility manages their power grid and what they consider resilience. But the thoughts will evolve. To give you an example, here a couple years ago, I was on a call with Sigray, and PGM was on the phone, and I asked them how they differentiated between what they call, or what we call resilience, and how they previously thought about reliability. And they thought about it for a second. And I said, well, one of the particular aspects that we think about now is the human element. If we have problems, do we have enough people, can they actually get to where they need to be helpful? And so the more of the, I'll call it a disciplinary differentiator, has become important in their considerations, because they understand resilience includes the human resilience aspect. But that's just one example. So there are a lot of metrics out there, and just important to catch the context of what they're going to be used for.
Good. Thank you, Dr. Craig. And for those who have additional questions, please shoot us an email at und.c2sr.und.edu. We can get those questions answered offline.